This is Truss example 4, and this one's a little harder. This I wouldn't call easy. The main reason it's not easy is that the top chord is not parallel to the bottom chord. And so when we take a section of this guy, we have unknowns acting in different directions. And so I can't easily write an fx or an fy summation to get a single unknown. This particular problem asks you to find the forces in D, E, and EF, which are these two. It doesn't tell you, but you need to realize that you need to analyze this joint here at E to get these two guys. And then the problem asks you to find the forces, this guy and this guy, which implies taking a section right here, and to find those three. Again, this is a truss that's loaded downward. It's going to bend downward. And so the bottom chord should be in tension. This top chord should be in compression. And these guys should kind of alternate tension and compression. We need the support reactions for both EY. And if we cut it here and take the left-hand section, we also need AY. Because all of our loads are vertical, and because all of our supports are vertical as well, then we can just say EY is equal to 3/4 of 800 plus 1/2 of 600, which is 600 plus 300, which is 900. And then AY is half of 600 and 1/4 of 800, which is 300 plus 200, which is 500. And again, the 900 plus 500 equals 1400, which is the sum of these two. And so it makes sense. You could write a moment equation to prove that, but in effect, this is what you get from the moment equation. So we have the support reactions. So let's do the joint at E to find these two unknowns. Let me draw the free body diagram of E for you. So the joint at E is the pin is here. EY is 900. The line of action of FE looks like this, and the line of action of DE looks like this. That's 45 degrees. So this is 6 and 6. So that's a 45-degree angle. And again, that's E, and that's F, D, E, and this is F, E, F. If we look at this as X and Y, if we look at this in the X direction, it's inconclusive. But if we analyze this guy mentally in the vertical direction with a 900-pound support reaction pushing up at E, then FDE is going to have to push down to keep this guy in equilibrium in the vertical direction. And so if FD is pushing on E, that makes FDE in compression. Once we decide that, then we can mentally look at the forces in the X direction. Our support does not have an X component. This guy has an X component to the right. And so FEF needs to act this direction to keep E in equilibrium. And of course, now that's in tension. And of course, that's what we expected. So we expected these guys to be in tension. We expected these guys to be in compression, which is what we got here. So that's the free body diagram. This is 45 degrees right here, 45. So coming back to joint E, keep in mind cosine 45 is equal to sine 45, which is square root of 2 over 2, which is 0.707. And you should remember that. You should remember this 0.707. So in the vertical direction, we've got 900 minus 0.707 FDE is equal to 0. So FDE is 1273 pounds, and it's pushing and it's compression. If we sum forces in the X direction, and we take to the right to be positive, then I have FDE times 0.707 minus FEF is equal to 0. And so FEF is equal to 900 pounds tension. So that's joint E. Questions on that? For the second half of this, we want to find the internal forces here. So we can use a left-hand free body diagram, or we can use a right-hand free body diagram. If we use the right-hand free body diagram, it would look like this. You can just lay a card here, and this is the picture that we're looking for. And then you can draw the unknowns on your card. And that would work, but that's a larger free body diagram with more details that you have to draw. On the other hand, you can use the left-hand free body diagram. And so if you put a card here, that's what the left-hand free body diagram would look like. This bottom chord is in tension. This top chord, we said he's in compression. This guy, we're actually not sure. And because these two are not parallel to one another, it becomes less clear what this guy is. In the method of sections is, well, it's true, it's joints too. If you're really not sure, it's usually best to probably draw tension. It's probably what's best. But let me go ahead and draw that free body diagram, kind of how I would do it. So we're going to draw this left-hand free body right here. So we're going to draw this triangle first. Our AY is 500. The bottom is in tension. And so this is F, G, H. The top is in compression. This is F, B, C. And the slope of this guy is 2/6, or 1/3. And so I'll call him 1/3. And the top of this guy is a square root of 3 squared plus 1 squared, so that's the square root of 10. So the horizontal component of this guy is going to be 3 over the square root of 10. And the vertical component of this guy is going to be 1 over the square root of 10. Finally, we need the diagonal, and we already said we're not sure what. And his angle is 45 degrees because he's 6 down and 6 down. And we'll label him as F, B, G, at a 1-to-1 slope. But we don't know his magnitude. We're not sure of his direction either. We're not sure whether he's pushing or pulling. Let's get dimensions on this. So this is 6. This is 6. Let's extrapolate him down to G, because we're going to use that. And that's 6 too. So this is our free body diagram, basically. Our directions are assumed pushing and pulling. So let's analyze this guy. So we come down here. Because our forces because our top and bottom chord are not parallel, we can't just write a sum forces X or sum forces Y to get a single unknown anymore. So that's what makes this a little bit harder. But what we can do is say sum moments about B, and that'll give us FGH. So if we sum moments about B, these two unknowns intersect there, so neither of them have a moment about B. So all you have is the 500 times 6 clockwise, and then the FGH times 6 counterclockwise. And so the FGH is equal to 500 pounds. We drew him in tension and he acts in tension, so he's 500 in tension. To find the next one of these, we can actually sum moments about G. And so this force intersects G, this force intersects G, and so we want to take the moment of this FBC about G and the 500 about G. If we leave FBC at B, then we have to resolve him into two components, into well, that's 2 over 6, but it's also 1 over 3. 1 over 3 and square root of 10. So it's 1 over 3 square root of 10. So the horizontal component is 3 over square root of 10, FBC, and his moment arm back to here is 6. And then we have the 1, the vertical component here, which is 1 over the square root of 10, FBC, and his moment arm is also 6. So you can do it that way. So basically, on this page here, if you slide FBC to B, there's two components. There's a 3/10 and a 3 over square root of 10 and a 1 over square root of 10. And then you have the 500, we're summing about G, and then you have the 500 times 12. And so if you take counterclockwise to be positive, then you have the 3 over the square root of 10, FBC, times its moment arm, which is 6. And that's counterclockwise, which is positive. And then plus the 1 over square root of 10, FBC, and his moment arm is 6. And then minus 500, and his moment arm is 12, about G. And so you get FBC is 790.6 by resolving them in the two components. But another trick that you can do is you can slide FBC back along his line of action and where he intersects this point C up here. And then when you're taking the moment arm of FBC around G, when it acts at this point, we have the component here, which is 3 over square root of 10. We have this component here, which is 1 over square root of 10, but the 1 over square root of 10 line of action goes through G, so I don't need that second component. And so I can just use the 3 over square root of 10, FBC, but if from this point, the moment arm is this distance, which is 8. 6 plus 2, which is 8. And so in this equation, I've got 3 over the square root of 10, FBC, times 8, minus 500 times 12 is equal to 0. So I get 790.6 from this equation. I get 790.6 from this equation. And so you can do it both ways, whichever way you can see. Finally, once we have this guy and this guy, now we can sum forces in the y direction to get FBG. And so we have, if we take up to be positive, we have 500 minus 1 over square root of 10, FBC, and then minus 0.707 FBG. Remember, he's at a 45-degree angle. So minus 0.707 FBG. And we can solve for FBG is equal to 353.6 pounds. We drew him in tension. He came out positive. And so our assumption of tension is correct. Remember, we assumed this. We weren't sure whether he acted down or not. So we assumed this. We wrote the equations based on this. He came out positive, which means our tension assumption was correct. Now, if we would have assumed this and did the calculations and it came up negative, that would mean that he really acts the opposite of what we assumed, which would be pushing, and in that event, he would have been compression. Finally, there's another way you can get FBG. And this is a little bit tricky. I wouldn't do this on a test, but if you're looking for a good time and think, well, what's another way I could work this problem? If you, and of course, you've already learned that we can extrapolate forces to points at which they intersect, even if those points are off of our free body diagram. So if you look at this picture, we can extend FBC out, and we can extend FGH out. And at some point, they intersect. And the question is, at what point do they intersect? Well, the slope of this FBC is 2 over 6. And this is 6. So when we go from here to here, he drops 2. We go from here another 6, he drops another 2. We go another 6, he drops another 2. And so actually, so the FBC will intersect this horizontal line at 6 plus 6, so 12 feet to the left of this support at A. 12 feet. And of course, FGH slides along his line of action. He passes through P at some point. And so if we sum moments about P, then FBC is not in that moment equation. FGH is not in that moment equation. And so all we have is the 500 and this guy. And if we leave this guy here at B, then we have to take his horizontal and vertical components. But if we slide this guy down to here, then this component is 0.707 FBG. This component is 0.707 FBG. I don't need to worry about the horizontal component. I can take the vertical, and then his moment arm is 6 plus 6 plus 12, so it's 24. And so then I can say 0.707 FBG times 24 minus 500 times 12 is equal to 0. And so I get FBG is equal to 353.6 pounds. I drew him tension. He came out positive, which means my tension assumption was correct. And so here we get the same number that we got here. And so you've got choices of equations that you can write, which if you don't like statics, you probably consider that maddening. But if you like statics, you go like, oh, that's fun. I can find another way to work that problem. So again, this is a harder problem because you got more angles going on. We can't easily write a sum forces x and y to get an unknown. We have to write more moment equations. And if you notice, we actually, for this guy, to work this guy, we actually basically had to write 2 different moment equations before we wrote a force summation. And so that made it a little bit harder.